Welcome. In this video, we're going to talk about vectors and the geometry of space, specifically a three-dimensional coordinate system. What you can see in this picture that I've brought in is the Cartesian coordinate system in a three-dimensional perspective. Now, the Cartesian coordinate system is a right-handed system, and when you think about visualizing it, think about holding out your right hand. Your fingers, if you curved them towards you, your fingers would point out towards the x-axis, your wrist is the right axis, and your thumb points up vertically, creating the z-axis, our third dimension. These are called rectangular coordinates because the planes that come together and meet, they all meet at right angles. So all of these axes, the axis where the x and the y axis meet down here, that is a right or 90-degree angle. Same between the x and z, as well as between the y and z axis. Those are all right angles. The perspective makes them not look as such, but they're all meeting at right angles. So this is a rectangular coordinate system. Now, if we think about graphing a plane here, if we think about graphing x equals 0, x equals 0 is the YZ plane. Call that the YZ plane. And that is the vertical plane through the Z and Y axes. So this plane that is showing up right here, which passes through, in a sense, we think about it passing through, it extends on both sides, but this vertical plane. So if we think about the front plane of this box right here, that is x equals some constant number. So if we were forward 3 units, that might be x equals 3. Or even if we took that plane and slid it back several units, that could be x equals negative something. You know, if it was back, the plane continued and we had some vertical plane like this. So a vertical plane, more or less facing where your fingers would point. Y equals 0 is the xz plane. So y equals 0 looks like this far left side of our rectangular prism. Okay. If we think about the far right side of this box, this vertical piece of paper, that shifted x, or in this case y units, out in the positive direction on that pi plane. So if we had shifted out, I don't know, what is that, 7, then this second plane I've drawn here would represent y equals 7. And I'm drawing these planes as a rectangle or a square, in perspective, of course, but they're not simply a rectangle or a square. They extend out. This extends out in all these directions, horizontally to the left and right, and then up and down. It's just we're drawing them as a rectangle so we kind of understand what's going on, or rather visualize the region. And if we think about z equals 0, that gives us the xy plane. And the xy plane would be like the base or the top of this rectangular prism. So right here, what I've highlighted on the bottom, that is z equals 0. The top also represents a z equals region, but in this situation, we may have counted up, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. If I were counting up 10 units, then this would be z equals 10. All right, that top plane. So really the point of what we're talking about here is just making sure that we can visualize and we understand direction and what the planes look like in this three-dimensional space. So I've pulled in another picture here. We can see that we have these three planes drawn. We have a blue, a green, and an orange plane. And they divide this three-dimensional space into 8 octants. We have 1, 2, 3, 4 quadrants. And because we're going above and below that XY plane, that creates these 8 octants. And further visualizing the XY plane, that gives us this sheet of paper, if you will, or plane, Z equals 0. The green plane here, that is my YZ plane, or X equals 0. And the orange plane is my XZ plane, or Y equals 0. So the last picture we were looking at showed us 3 planes going through the origin. So now if we look at 3 planes, say intersecting at the point x equals 2, y equals 3, and 5 equals z. All right, so we're used to seeing an ordered pair. In 3 space, we deal with an ordered triple, and that order is important, x, y, z. So x being 2, we have a plane, x equals 2. And remember, if we were to hold up our right hand and kind of curl the fingers towards us, that x equals plane is facing the way my fingers would point. It's facing out towards us. We have y equals 3. The y equals plane would be facing towards our wrist or our arm. Right? So we've got this red plane, y equals 3. And then the z plane, z equals 5. That's going to be vertical. And you'll notice instead of going through the origin, these planes are shifted. My green plane has moved out 2 spaces from the origin, x equals 2 in the positive direction, so forward from the origin. My y plane has moved out 3 units from the origin, and my z plane has moved up 5 units from the origin. Okay, and so that ordered pair is the solution where all of those planes are intersecting. So I hope that gives you a better idea into the 3 space and what it looks like when we're graphing. Here we're going to look at a few examples where we interpret an equation or an inequality geometrically. Our first example we have is z greater than or equal to 0. So what we want to realize is that z equals 0 is going to be a flat plane running through the origin, right? A flat plane. So z being greater than or equal to 0 would represent everything above going up infinitely. So I'm drawing it as a cube, but you know that this cube extends out in all directions, although it does not go down, right? So it's stopping at the XY axes and just extending up. Our next example is y equals -2, z equals +2. Y equals -2 would be vertical. We would sketch back 2 on our y-axis, and we would have a plane that looks roughly like this. It's running through this point here. Okay, so that's my y equals -2. And z equaling +2, that would be a vertical plane which runs through z equals 2. So we shift up and we have this plane here that looks roughly like this. And where these two planes intersect, they're intersecting on a line which is parallel to the x-axis. And that line would have the point on it, 0, -2, and 2. You might want to get some practice visualizing these. I'm sure if you go on the internet, fiddle around or search a little bit, you can find a 3-space grapher that might help you think about visualizing these situations. So one more example. So here we have 2 more equations, x squared plus y squared equals 4, and then the plane z equals 3. X squared plus y squared equals 4 is a circle of radius 2. X squared plus y squared equals r squared. And if we were to think about this in our 3 space, knowing that we've got down, above, and below in all these directions, we would have a circle of radius 2 in that xy plane. X and y are like that. So we've got a circle of radius 2. So it's a circle of radius 2, although now we have to think about, well, we've got this z equals 3 portion. And z equals 3 is going to raise that circle up 3 units. So instead of the circle being on the xy plane, it's actually a circle 3 units above the xy plane. All right, so it's still a circle of radius 2, and this point would be 0, 2, 3, or we'd have a point over here, which would be 2, 0, 3. Okay, so the 2 equations that we were initially given, they represent this circle, but instead of being directly on the xy plane, the z equals 3 moves it up 3 units above the xy plane to z equals 3. And because I'm not excellent at drawing these 3 spaces quickly, I've brought in the picture from our book. So again, you see that circle of radius 2, and then it's extrapolated up 3 units. So that concludes our discussion of understanding this 3 space. Moving forward, we're going to talk about distance between points in space, as well as a sphere, the standard equation of a sphere in space.